Now let's do a sample problem and see if we can use what we've learned to solve this horrible looking collection of capacitors here. We've got a whole bunch of them, 9 of them in total. We want to know what one capacitor could replace them, and it looks almost impossible. It's such a mess. But the way to handle problems like this is to look at little pieces at a time and redraw it until you get it down to one capacitor. So, for example, the top 3 capacitors are in series, and we know how to combine those. So we can replace them with one that we'll call CA. And we know it's 1 over CA is 1 over C1, 1 over C2, 1 over C3. We punch this into the calculator and we get an equivalent of 54.55 nanofarads. So that's going to replace these 3. Now what about these 2? They're in parallel, so we know we just add those. So the B capacitor will be 400 plus 500, which is 900. So these 2 get replaced by a single 900 farad capacitor. Then down here at the bottom, these 3, these are in parallel. We know we just add those. So we'll get 700 plus 800 plus 900. That gives us 2400 nanofarads or 2.4 microfarads. So now we can redraw the capacitor, like the circuit like this. We've got just CA, CB, our 6 capacitor, which was by itself, and CC. These are all in series. We put them together, and we get 46.46 nanofarads. Notice again, it's smaller than the smallest one, which is what we expect. So this circuit looks to the battery exactly the same as this mess. So that's the advantage of being able to combine these. We can figure out what would the charge on this capacitor be. We just use Q equals CV to find out. We take this, multiply by 12, we get about 558 nanocoulombs. What that also means, though, if that's the charge on this capacitor, that must be the charge on all the capacitors that were in series. This one, this one, this one, and this one. They must all have 558 nanocoulombs across on them. Now we could find the voltages on each of the first 3 capacitors because we know, for example, Q equals CV, and we know that whatever the charge was on the replacement for these, the 558, it's the same charge on each individual capacitor. So for the first one, 557 nanocoulombs divided by its capacitance, 5.575 volts. The next one, bigger capacitor, so smaller voltage required for the same charge. That trend continues for the third capacitor. We're at 1.858 volts. Then capacitors 4 and 5, we can find the voltage on them. This is our equivalent capacitance. That's our charge. We get 0.6194 volts. That voltage is across each of these, remember, right? Because they're at the same potential. What about the voltage across this? The 600 nanofarad. We would do our same charge that we keep seeing divided by 600 nanofarads, so it's just under 1 volt across that. And finally, what about the bottom 3 capacitors? Well, we would get our charge divided by our equivalent capacitance. We get this less than 1/4 of a volt. And that 1/4 of a volt is across each one of these. We could now find how much charge is on each one of these. We know what charge is on the total, but how is it split up between them? We just use Q equals CV to figure that out since we know the voltage. Now, what do we get if we add all the voltages? Well, we can't add the same voltage multiple times. For example, we don't add these 3. They all represent the same thing. So we don't add that. But we add 0.23 plus 0.92. Again, we don't add these 2 twice. They're in parallel. Plus 0.619 plus these. When we put all of these together, we get 12 volts, which makes sense. We have to get that. Now, what about the charge stored on the capacitor? What does it represent? It represents potential energy. We use this to do work. We store energy there and we extract energy from there. We need to know what's the energy stored in the capacitor. We know that if we move a charge through a potential difference delta V, it takes amount of work Q times delta V. However, as we add charges to the plates, delta V changes. Then we're finding the area under a curve of Q versus V. If we were doing calculus, we'd say we just do this integral. But since we're not, the area under this triangle, this Q versus V is going to be CV versus V. That's going to be a line. We're just going to get a right triangle, and the area is 1/2 CV squared. So this is the energy stored in a capacitor. It just depends on the capacitance and the voltage between the plates. Now, it turns out capacitors aren't great for energy storage. They're really good for power storage. The difference is, the difference between those two ideas is why we use them for things like flashes and disposable cameras. There's a lot of stored energy in the battery, but it can only be released slowly, as fast as the chemical reaction can happen. The capacitor, on the other hand, can release the energy much more quickly, so we can use the battery to slowly charge up the capacitor and then let the capacitor dump all that energy at once to fire the flash. It's not necessarily high energy, but it is high power. This is why you can't take a flash camera and just fire the flash over and over and over again. You have to wait a bit before it can be used again. When you see this on TV shows all the time, a defibrillator where they shock a patient to restart their heart. The battery charges the capacitor, they shock the patient's heart, and then they have to wait a few seconds, number one, to see if the patient has come back, but number two, for the paddles to charge up again. Being able to charge and discharge very quickly would make capacitors much better than batteries for electric cars. It could be recharged much faster than even a gasoline car could be filled if you have a large enough power supply. And there's not really a set limit on the number of charge-discharge cycles. So this car made of capacitors instead of batteries could be faster than the fastest Tesla as long as you had motors that could stand it. The problem is the energy density. To find that, we could take this energy and divide it by the volume of the capacitor. Well, how do we know the volume of the capacitor? If we're using a parallel plate capacitor, the volume is just plate size times separation. So we put this in the formula for C, or we put in the formula for C, we divide by this, and we can write this as 1/2 epsilon times plate voltage over separation, which is the same thing as electric field. For supercapacitors, right now they have an energy density about 1/10 that of lithium-ion batteries, and we know that batteries in general have a smaller energy density than gasoline, but they are improving. This may eventually change because there's a lot of work being done on making better capacitors. These things are used in regenerative braking systems, and that's part of the reason electric cars are so good in terms of fuel economy. When the car stops, rather than that energy going into waste heat, it's dumped in a capacitor quickly, and the capacitor can then slowly trickle it back into the battery and keep it charged.